This is section 7.3, part B, the central limit theorem. Most population distributions are not normal. The household incomes, for example, are strongly skewed. Yet from the previous work with household incomes, the distribution of means for the samples of size 100 is approximately normal. What is the shape of the sampling distribution of X bar when the population distribution isn't normal? So if we go back to that same internet applet where we looked at the different shapes, you would still use the same concept. You would put in, instead of starting with a normal distribution, you would start with a skewed distribution. You would take different sample sizes and you would see what the distribution of the approximate sampling distribution would look like. So it's a remarkable fact that as the sample size increases, the distribution of X changes shape. It looks less like the population and more like a normal distribution. When the sample is large enough, the distribution of X bar is very close to normal. This is true no matter what shape the population distribution has, as long as the population has a finite standard deviation, sigma. This famous fact of probability theory is called the central limit theorem. So the central limit theorem tells us that if we draw a simple random sample of size n from any population when the mean is mu and we have a finite standard deviation sigma, the central limit theorem says that when n is large, the sampling distribution of the sample mean X bar is approximately normal. How large a sample size n is needed for X bar to be close to normal depends on the population of distribution. More observations are required if the shape of the population distribution is far from normal. In this case, the sampling distribution of X bar will also be very non-normal if the sample size is small. So you should be cautious. Be sure you understand what the central limit theorem does and does not say. We use the Rice University sampling distribution applet to create a population distribution with a very strange shape. So here is the population distribution. So below, the first picture is when we take a sample size of 2. The second one is when we take a sample size of 5. The third one is a sample size of 10, and the fourth one is a sample size of 25. So as you can see, as n increases, the shape becomes more normal. The mean remains at mu is equal to 13.5, and the standard deviation decreases as n increases. As the previous example illustrates, even when the population distribution is very non-normal, the sampling distribution of X bar often looks approximately normal with sample sizes as small as n equals 25. But to be safe, we're going to say for the central limit theorem that n needs to be at least 30 for this to be normal. With this issue settled, we can now state that the normal condition for sampling means. So our normal conditions, if the population distribution is normal, then so is the sampling distribution of X bar. This is true no matter what the sample size is. If the population distribution is not normal, the central limit theorem tells us the sampling distribution of X bar will be approximately normal in most cases if n is greater than or equal to 30. The central limit theorem allows us to use normal probability calculations to answer questions about sample means from many observations, even when the population distribution is not normal. Your company has a contract to perform preventative maintenance on thousands of air conditioning units in a large city. Based on the service records from previous year, the time in hours that a technician requires to complete the work follows a distribution whose density curve is shown below. This distribution is strongly skewed to the right. The most likely outcome are close to 0, and the mean time is mu is equal to 1 hour with a standard deviation of 1. In the coming weeks, your company will service a simple random sample of 70 air conditioning units in the city. You plan to budget an average of 1.1 hour per unit for a technician to complete the work. Will this be enough time? Follow the 4-step process. So remember, on a 4-step process, the first thing we do is state. So for our state, we can say, what is the probability that the average maintenance time, X bar, for 70 units exceeds 1.1 hours? Next is our plan. For our plan, we're going to know that the sampling distribution of the sample mean times, X bar, spend working on 70 units has a mean of the average of the X bars is just equal to the average of the population, which is 1 hour. We need to check to see that the 10% condition is met before we find the standard deviation. Now, if we do 10 times those 70 units, that's going to give us 700 air conditioning units. If this is a very large city, we can about guarantee there's going to be more than 700 air conditioning units in the city, so this will meet the 10% condition. So now we can find the standard deviation. Remember, when you go to find the standard deviation, our formula is the standard deviation of the population divided by the square root of n, where n is your sample size. So if we do 1 divided by the square root of 70, that's going to give us a standard deviation for our sample of 0.12 hours. We need to check to see if the normal condition is met. Now remember, to do this, you're going to do n times, we're going to see what our n value is. It needs to be at least 30 to make sure that even though our original population is not normal, that we can still use the normal conditions here. So since our sample size is 70, we know that's at least 30 or higher, so we can approximate using the normal conditions. So we can say that the distribution of X bar is therefore approximately normal with a mean of 1 and a standard deviation of 0.12, and we're going to find the probability that X bar is greater than 1, or greater than 1.1, because we want to see if it exceeds 1.1. So the next thing we're going to do is the do part of this. So we're going to determine the probability that X is greater than 1.1. So for this, we're going to use our z-score. Remember, z is X minus mu over sigma. So we're going to do 1.1 minus 1 over a standard deviation of 0.12, and that's going to give us a z-score of 0.83. Now remember, when you use your z-scores, 0.83 is going to be around here. The table tells you the area or the probability that is less than that value. So if you look up 0.83 on table A, it's going to give you an area of 0.7967. But we want to see what exceeds that, or what is greater than that. Now the whole area is 100, or 1. So you would have to do 1 minus the area on the table to find the probability that it exceeds 1.1. So for our conclusion, we can say if we budget 1.1 hours per unit, there is a 20% chance that the technician will not complete the work within the budgeted time. You will have to decide if this risk is worth taking or if you should schedule more time for the work.